So welcome to lecture. So again, we're picking up here with chapter 17, and this should be our last chapter of the season here. Huh? So chapter 17, which is equilibrium. Again, the notes are up there somewhere where the final review material is, in case you couldn't find it, but that's where you should be able to find it up on Canvas. And this will be the last chapter here. And like usual, if you do have any questions throughout the lecture, feel free to obviously ask them there in the chat box, and we'll definitely get to them and stuff like that. So in this last chapter, we're going to talk about equilibrium. Equilibrium involves a certain type of reaction, and that certain type of reaction is reactions where we have these arrows that head basically in both directions, and these are reversible reactions. And as we probably have talked about, I think before, previously, a little bit earlier on in the semester, it has two directions. It has the forward direction and this type of reaction where it goes from reactants to products. But in these sort of reversible reactions, at some point, once you sort of build up enough of the products, the opposite reaction can occur where the products will actually come together and actually make back some of the reactants. And that's what's referred to as going in the reverse direction. And at some point, as we'll talk about here, this reaction will come to what is commonly referred to as chemical equilibrium. And chemical equilibrium basically means, as we will see here, is the rate of the forward reaction will equal the rate of the reverse reaction in this case. So basically what that means is just as quick as it goes to the right, those guys will sort of recombine and just as quick kind of head back to the left. And as we'll see and as we'll talk about, again, important to keep in mind when a reaction, for example, reaches chemical equilibrium, sometimes people think that's the point where you have pretty much the same on both sides. So you have the same number of reactants, same number of products. And again, it doesn't necessarily mean that. It means that when it reaches chemical equilibrium, it's the point where the rate of the forward reaction will equal the rate of the reverse reaction. So essentially, the way you could think about it is if it reaches equilibrium, for example, and at the point where it equals equilibrium, just randomly here, A is equal to 4, B is equal to 3 at that point. Again, these are just made up numbers, maybe concentrations, maybe pressures, whatever it may be. And let's just say C was 2 at that point, and D was 1 at that point. And what it means is, again, when it reaches chemical equilibrium, they basically will be able to maintain those concentrations because, again, as quickly as it goes to the right, those guys are going to come back to the left. So it's going back and forth basically at the same rate, which means essentially everybody on the reactant side, everybody on the product side, essentially will lock themselves into their concentrations at that point, and not much will change because, like I said, as quick as it goes to the right, goes to the left, and everything just sort of balances out in that sense. So when we say chemical equilibrium, again, we're really talking about is what I wrote down here, and we'll see it in a bit here again, I think, is the rate. And it's the rate of that forward reaction equals the rate of the reverse reaction. Again, when we reach chemical equilibrium, it does not necessarily mean that we got exactly the same amount on both sides. It just means wherever they're at that point, they will basically maintain their concentrations, they'll maintain their pressures because there's not an overall big change that's occurring. So first, though, we're going to talk about sort of chemical reactions and sort of how they occur and some things that affect the rates of reactions and how they occur. So the first idea is what is sometimes referred to as collision models. So the idea here is pretty simple one. In order for a reaction to take place, so in order for when you go from, say, reactants to products, right? Pretty much everybody on the reactant side has to break all those bonds. Right? And everybody on the product side has to make some new bonds. But in order for these guys to break, essentially a reaction has to sort of be initiated by some type of collision. So you essentially will need molecules to come together and essentially collide with each other. Now, also important to remember is that not all collisions of reactant molecules, for example, will actually lead to products being formed. There's a couple of sort of things that has to happen when these molecules sort of come together on the reactant side and collide with each other for sort of products to be formed. First off, the oxygen has to hit each other, but they do need to hit each other sort of in the right location, sort of like an active spot, if you will. So, if those two molecules up here, for example, they come and collide in each other in sort of the wrong location, nothing much is going to happen. But if they do sort of collide with each other in the right location, sort of the active spot in both of those things, then probably products will occur. The second important thing is when these things sort of come together is they actually have to come together with the right amount of energy. So they has to come together when they collide with that right amount of energy, basically to allow them to start to break apart and make these new bonds. And the rate will depend on the concentrations of reactants and temperature. So concentration is really important. If you think about concentration and sort of the rate of the reaction, when we talk about the rate of the reaction, what we're talking about is how fast or slow a reaction will take place. And obviously, if we do something like increase the concentration of the reactants, what that's going to do is pretty much usually increase the rate of the reaction, because now if you have a whole bunch of these guys kind of floating around, there's a pretty good likelihood that they will come in contact with each other relatively quickly, as opposed to if you had a very low concentration, you got like, three kind of spread out. It's going to take longer for those sort of molecules to find each other and sort of initiate a reaction to take place. So when we sort of increase the concentration, as we'll talk about, typically that will increase the rate of the reaction, and vice versa. If you kind of lower the concentration, typically the reaction rate will sort of slow down, because again, they're out there kind of searching for somebody, like in a desert, like you maybe see somebody over there, as opposed to, if everybody was in a small closet or something together, they're obviously going to run into each other a lot quicker. Temperature is also important, and temperature plays a really big part in the idea of the energy aspect of when these guys come together, that they need the right amount of energy. Obviously, if we increase the temperature, a couple of things usually will happen. Even these guys that maybe are far away will now be moving a little bit faster, right? Because they have a little bit more energy. And thus, when they also do come together, they will come together with more energy, which will allow them to pretty much have the correct amount of energy for a reaction to take place. So there's a lot of things that, affect the rate of the reaction. And typically, as we will also talk about here, if you increase the temperature, typically the rate of the reaction will also increase, and vice versa. If you sort of lower the temperature, everybody has a little less energy. They're moving around a little bit kind of slower, you know, and when they do come together, they have less energy when they collide and may not lead to products being formed. But when a reaction takes place, so if we have these two molecules here, they're going to come together and collide. And what's going to happen is at some point, you'll get this sort of intermediate here. which we'll see in a sort of a diagram. And this is sort of what is referred to as sometimes an activated complex, or a transition state complex. And we'll talk about exactly kind of where that is in a little bit here. But it's essentially a molecule that you have sort of bonds that are partially being made, and you also have bonds that are partially being broken. So you got this sort of intermediate that happens in this process when a reaction takes place of, well, we need to start breaking all the bonds on the reactive side, but in the same sort of aspect, we need to start making some of those new bonds. And there's usually this sort of, like I said, I don't know, intermediate is maybe the right word, but there's usually this sort of complex that you end up with in the process of this sort of situation that's happening, where you get this guy that has these partially made bonds, partially broken bonds. And as you can see, at some point, they will then end up over here in some new molecules on this side. So, you know, this is sort of our products over here, right? This is sort of our reactants. And this is sort of the progression of the reaction taking place and sort of what's happening in terms of energy and bonds. And we're going to sort of talk about a lot of the aspects of this in this chapter. So let's talk about sort of the idea of concentration and temperature. Again, concentration typically will increase the rate because more molecules would lead to obviously more interactions and more collisions occurring. So as I drew on the last page, again, increasing that concentration, like in a beaker, for example, right? You have a very high concentration. Again, they don't really have to float around very long to come in contact with somebody. Again, if you had sort of a beaker and you had sort of just a sparse amount of guys in there that can react, again, it's going to take a little bit longer for them to all come together. And usually, again, the opposite would be there. It'd probably be a much slower sort of rate. Usually ions, by the way, when you have a solution, you got ions floating around, you know, ions usually react pretty quickly because, you know, they're in solution, they're moving around, they're able to react, as opposed to if you had sort of a solid sitting there, you know, not much is going to happen with the solid unless you kind of help it along and stuff like that. So we can sort of increase the rates of reactions with solids by, you know, grinding it down, kind of providing a greater surface area for the solid to react is ways that you could kind of increase the rate of a solid in reaction. And temperature, as I mentioned on the last one as well, again, at those higher temperatures, you have those higher speeds and you have more molecules that essentially have the right amount of energy to help break those bonds and start forming those new bonds. And that usually results, again, in a faster reaction. So on the generic sort of scale, if you increase a reaction by like 10 degrees Celsius, usually the rate of that reaction will usually double. Not all reactions, but in general, if you kind of just take the temperature up by 10 degrees Celsius, usually what you'll see is that particular reaction will sort of double in the rate of how fast it will actually occur. So let's talk about sort of this process of energy and reactions that occur. And, you know, we can look at some energy diagrams here. And just to remind, I'll do it here. Just to remind everybody, there's a couple different types of energy diagrams as you sometimes will see. So if we draw one, for example, like this. This is our products. Over here are reactants. And this is energy. So in this particular energy diagram, wonderfully drawn, we have our reactants that are higher in energy. then our products. And again, the way you can kind of think about it, in order for our reactants to get down in terms of energy to our products, in this case, energy has to be given off. And this is an energy diagram for a exothermic reaction. Remember, exothermic means heat and energy is released. And if you remember when we did all of those sort of calculations with heat and energy, that is usually when we have like a Q that is negative, right? Or a delta H that is negative. Those imply exothermic type reactions. The opposite of that would be an energy diagram that would be more endothermic. And if we sort of look at one of those, again, it looks kind of similar. Again, this would be energy. The difference is here, very badly drawn. There we go. Products are reactants. And in this particular case, that's reactants, badly worded. Our reactants are actually lower in energy. Than our products. So again, if you sort of think about in order for our reactants to get up to our products, the energy has to be put in. So energy has to be absorbed. And remember that when you absorb energy, that is an endothermic process. And that is when heat is absorbed or energy is absorbed. And that is when we talk about sort of Q, which is heat, right? It's a positive number. Delta H, which is enthalpy, also a positive type number. So whenever you see an energy diagram where your reactants are higher in energy than your products, that usually will indicate it's an exothermic reaction overall. You will also see a reactants that are lower in energy than your products. That's an endothermic reaction when you look at an energy diagram. Any questions on that? Now, there's really an important aspect to each of these diagrams and what happens in a reaction, and that is this amount of energy here, from where our reactants start to sort of the top here of the curve. And this is what is known as the E of A, which is our activation energy. And the activation energy is the minimum amount of energy that's basically required for a chemical reaction to occur. It is, as you can kind of see in this diagram, it's the hill that the reactants need to climb basically to get to the other side. And if we look in our endothermic one over here, this would be our activation energy. And we could see that for sure the bigger activation energy occurs, as we can see here on the right, which is our endothermic reaction. And that makes sense. This is an endothermic reaction. We kind of have to put energy in to help those reactants up and over to the other side. As opposed to our exothermic on the left, we have a much smaller activation energy. And that means that, you know, we don't need as much energy to get up and over that hill to the other side. Activation energy plays a really important part in terms of the rate of a reaction. So the larger the activation energy, usually the slower the reaction. And the smaller the activation energy, usually the faster the reaction. Again, the activation energy is that hill has got to climb to get to the other side. So if you have a really big hill, it's going to take longer for everybody to get up and over to come to the other side, as opposed to if you had a smaller hill, those guys, more guys get up and over really to the other side a lot quicker. So usually the larger the activation energy, the slower the reaction will take place. Now, when we get to the top of the hill, And we'll just use their little picture here because it's nicely drawn. When we do get to that top of the hill, remember, as we were talking about before, as this reaction is taking place, we got to break all these bonds here on this side for our reactants, right? And then we need to make all these bonds on this side for our products. And when we get to the very top of the hill, this is again what is sometimes referred to as the transition state. And at the transition state, that is where we have what I was saying earlier, what is sometimes referred to as the activated complex, or is sometimes referred to as the transition state complex. And this is a substance or a species where, as we were talking about earlier, we're breaking some bonds. So we got some partially broken. So partially broken bonds there. We have some partially made bonds here. And we have this really activated complex that has these partially made bonds, partially broken bonds. And because they have these bonds that are sort of in transition, which is why I sometimes refer to as a transition state, is we have these guys that are eventually very, very high in energy. So on each of these diagrams that we see here on the right, and also the ones that we drew over here on the left, our transition state will always be up there at the top of the curve. And these guys usually are very, very hard to isolate, these sort of transition state complexes, because they are high in energy. And one thing that we should remember from the semester, right, is things that are high in energy are not all that stable. Yeah, they're not very happy being high in energy. Everybody really wants to be sort of low in energy, or a lowest state of energy it could achieve. And because that's, as you can see on this curve, really the highest point of where you're at, it's very high in energy, and it really doesn't hang around a very long time because it's very sort of unstable in that sense. So usually as it's climbing up this hill, it will usually very quickly sort of drop down to the other side, you know, to our products, as that transition state guy really won't hang around a very long period of time because it's, again, highest in energy. If we look at our diagram here on the right, we see our products, our reactants are higher in energy than our products. So we would know that this is an exothermic reaction. And again, our activation energy would be the hill that occurs in terms of energy from the reactants to the top of that hill. And that really is the minimum amount of energy that's needed. So when we talk about these guys coming together and colliding, in order for really a reaction to take place and products to be formed, they need to collide with at least the amount of energy that's required for them to get up and over that hill of activation energy. Any questions on that? Now, one way that we can typically sort of increase the rate of a reaction is to add a catalyst. So another way that you could kind of speed up a reaction is to add a catalyst. A catalyst, which oftentimes in equations are found up here on the arrow. So sometimes, you know, they may put something like platinum, you know, they may put H plus, like an acid catalyst. There'll be something written on the arrow. And that usually implies that that thing is a catalyst. And a catalyst is not considered a reactant, and it's not considered a product. So it's really not a reactant. It's not a product. And it's actually not even used up in the reaction. It's actually there at the end of the reaction, just like it was at the beginning of the reaction. Really what a catalyst does is its sole purpose is to allow a reaction usually to occur faster. And that's usually what we think about when we think about catalyst, is a reaction occurring faster. In reality, there's actually some catalysts that can slow down a reaction, but probably 9 times out of 10, if somebody's talking about a catalyst, even maybe more than that, 9.9 times out of 10, if they're talking about a catalyst, they're usually talking about it in the sense of speeding up a chemical reaction. So how a catalyst essentially is able to sort of speed up a chemical reaction is, you could think about it this way: it sort of provides a platform, if you will, for everybody to come together in a more efficient manner. So instead of without the catalyst, everybody's perhaps got to float around and try to find each other. You add a catalyst into the mix. What it could sometimes do is provide, literally sometimes there's solid catalysts, literally could provide like a platform that allows, oh, I want to come this way. The other guy decides, oh, I want to come this way towards my catalyst. And now what you've done is bring these two guys together a lot quicker than you would if the catalyst wasn't there and they were just kind of floating around by themselves trying to find their way to each other. So a lot of times a catalyst will provide that more efficient way of everybody to come together. And in terms of how it's able to sort of speed up the reaction is by finding this alternative path for this reaction to take place, kind of like the old Wile E. Coyote and Roadrunner cartoon. One goes up and over the hill, right, to get to the other side, the mountain, and like the Roadrunner opens up the door and the mountain just goes straight through to the other side. Obviously, the Roadrunner could get through a lot quicker. It's sort of the same idea. By finding this alternative path, what a catalyst essentially will do is what we see here in this graph. A catalyst will lower that activation energy. And by lowering that activation energy, what it will essentially do is allow a greater proportion of molecules to have enough energy to get up and over basically to the other side. So in the uncatalyzed reaction, as we can see there on the top, these reactants would have to have enough energy basically to climb this hill to get to the other side, right? And in the catalyzed reaction, by lowering that activation energy, now those reactants only need to climb basically this hill, which is much smaller. So what you're going to be able to get, again, like I said, is a greater number of molecules that are able to have that sufficient amount of energy to go from the reactants to the products. And the result of that is we will see the rate of the catalyzed reaction be greater than the rate of the uncatalyzed reaction. So this is truly, a very sort of efficient way for a reaction to take place. If you want to kind of speed it up, you can add a catalyst. And again, that will allow this reaction to take place a lot quicker. For example, the production of ammonia, when you take N2 and H2 together to make ammonia NH3, that is a spontaneous reaction. And a spontaneous reaction means nothing more than if you leave those guys together, the H2 and the N2, they will eventually come together. Doesn't mean that it will happen fast, may not happen, may happen slow, but eventually they'll come together. And in that case, it actually would happen very, very slow. But if you add a catalyst to that reaction, it can happen very sort of quickly and more efficiently, and it will occur a lot sort of better in that sense. You don't have to wait all day for it to occur. Any questions on catalysts and how they affect the rate of a reaction? Okay, so now that we talked about sort of rates of reactions and sort of how they occur, we are now going to get into equilibrium. And when we talk about equilibrium, as I talked about at the very beginning, what we are essentially talking about is again, that reversible reaction where it has two directions. And again, when it reaches that chemical equilibrium, what it means is the rate of the forward reaction going from reactants to products will equal the rate of the reverse reaction where we're going from products back to reactants. So as I mentioned at the beginning, essentially what that means is, again, it does not mean that if you reach equilibrium, you have the same amount on both sides. It just means because as fast as it goes one way and comes back the other way, they're basically equal to each other. Everybody will pretty much lock into place in terms of their values when it does reach equilibrium. Very common equilibrium that we have seen a lot is actually phase changes. So when we talk about sort of phase changes, like we have here in this picture, this is the process of evaporation and condensation, right? And that happens normally at the boiling point of a substance. So for example, at water, which is 100 degrees Celsius, right, for water, at 100 degrees Celsius, exactly at 100 degrees Celsius, we have both the liquid state and the gas state in equilibrium with each other. And again, exactly at 100 degrees, that's when evaporation occurs, right, going this way. And at exactly 100 degrees, that's when condensation occurs, going the other way, going from gas to liquid. Remember that exactly at 100 degrees, that is when we have both of those phases in equilibrium with each other. And what that means is both phases are actually present at that point. And that's what happens basically at the surface of any liquid, like I think we might have talked about. At the surface of any liquid, you know, there's a constant process of where liquid guys are jumping out into the gas phase, and you got some gas molecules dropping back into the liquid phase. And in terms of water, for example, it's not until you truly get over 100 degrees Celsius that you kind of convert into gas or steam. And it's not until you're a little under 100 degrees Celsius that you truly kind of convert into liquid water. Same sort of thing happens at the equilibrium process when we go from solid to liquid and back, right? Solid to liquid is the process of melting, and freezing is going the other way. And again, for water, this happens at 0 degrees Celsius. So again, exactly at 0 degrees Celsius, that is where we have both phases said to be in equilibrium with each other. So we have a little bit of solid at that point. We have a little bit of liquid at that point. And again, that is like your ice crystals that we talked about. If you remember when we talked about energy and stuff like that, nice line. That's when we use things like the heat of fusion and the heat of vaporization, which I think we talked about when we're doing like specific heat and those type of stuff. And again, there's a certain amount of energy required just to kind of do those transitions. But equilibrium between the different states is very common. And again, it will maintain that equilibrium at that particular temperature. And again, it's not until you get a little above 0 that you have liquid water, a little below 0 that you technically have solid. Now, when we think about equilibrium, and for example, if you did a reaction that was a reversible reaction and it reached equilibrium, you may look at the beaker, for example, and it may just look like, well, not much has changed. And you keep, come back. You could be staring at this beaker after the reaction is done. You see maybe a change of color. Maybe it goes from like a colorless color to a red color or something like that, or goes from a red color to colorless. And at some point you just sit there and sort of stare at the beaker and nothing much looks like it's changing. And you may think, oh, this reaction's all done. And sometimes we think about it in that sense as like a one-way street, like everything just went to the products and the reaction's over. But remember that these are reversible reactions. So although visually on sort of the macroscopic level, when we look at it, we may not be able to see much that's happening, we may not be able to see much that's happening. There is a lot that is going on. So if you could sort of super zoom in on the solution, you would see a lot of activity. You would see people going from reactants to products and products to reactants. Everybody good on the? Everybody could hear? Yes. Okay. All right. So so again, if you could look at this reaction that's at equilibrium. Okay, good. Perfect. All right. So again, if you're having some trouble, just hang in there. Hopefully it'll come back. If not, you could always log out, come back in. Maybe that might fix it. So you can give that a try. So when we look at a reaction that's reached equilibrium, like I said, so on the big scale, it may not look like much is happening. But if you were able to sort of super zoom in, you would see a lot of activity. You'll see guys going from reactants to products, guys going from products back to reactants. But essentially what's happening is, because it's reached equilibrium, it's happening at the same rate. So in sort of the big picture, when we look at it, we don't really see much happening. But again, if you were to basically super zoom in, it would be very dynamic on the microscopic level. There's a lot of activity that's happening. But again, on sort of the bigger picture, when you say look at a beaker, it may not look like very much is happening at all. But again, there is a lot of activity that's happening. It's just happening at the same rate. So in a reaction of H2O plus CO to make CO2 and H2, again, at some point, what we will see is it will reach equilibrium. And at that point, again, these guys are going to lock into basically where they're at when it reaches chemical equilibrium. And as you can see here, in terms of the numbers, you don't have the same numbers on each side. It just means as soon as they lock into equilibrium, they will eventually maintain their numbers. When we start a reaction that's reversible, as you can see here, these are our reactants here. These are our products, these two guys on the bottom. And obviously, when the reaction starts, it's really going to start in a one-way direction because it only has reactants. So it's got to go, towards the product side. At some point, you'll eventually start making enough products that, in addition to this reaction heading towards the products, you will start to get this reaction kind of heading the other way. And at some point, when it does start heading in both directions, like here at the end, we will have the rate heading in both directions be equal to each other, locking everybody into place. So a lot of times when we do start the reaction, for example, because we're only kind of starting with reactants, it does force the reaction to head towards the products and almost a one-way street. But because this is a reversible reaction, it's able to start building up those products, which will kick off the reverse reaction until, again, everybody's basically heading back and forth in the same direction. And that's what we see graphically when we look at a reaction like this. Again, at the beginning of the reaction, we have mainly reactants and pretty much no products. So as this reaction proceeds, the forward direction is going to dominate. And we will start to use up some of our reactants as that forward direction starts. It will also then start to build up some of our products. And again, at some point, our reverse reaction will take place. Until when you look graphically at it, you hit that point where everybody plateaus together. And what that means is that is the point when chemical equilibrium has been reached. that point where this little dotted line is, that rate of the forward reaction will equal the rate of the reverse reaction. So again, it's sometimes a little slow process. You got to sort of kick off, the forward direction to allow products to be made to come back the other way. So concentrations reach levels when the rate of that forward reaction equals the rate of the reverse reaction. And as we've been talking about, that is essentially when everybody sort of gets locked into place. So if we look at this particular reaction here, this reversible reaction, and if we add more H2, how does the concentrations of everybody compare to their original concentrations in this particular reaction? So when you're looking at something like this, you want to think about what's going to occur when we add something, in this case, like water. When we add water here, water essentially would be added to the left-hand side of the reaction. And what we should expect in this case is we have now increased the concentration of our water, which means, as we talked about earlier, if we increase the concentration of our water, there's more reactants here. So there's going to be more waters and CO that could come together at a much quicker rate because, again, the CO doesn't have to go try to find a water. The H2O is there. It can find it relatively quickly. And what that's going to do is when we add more of that water, it's going to really kick this reaction off heading in this direction, heading towards the products. Because, again, we have more water, going to allow it to react with the CO. It's going to initiate that forward reaction to take place. So what does that mean in terms of the concentrations of everybody in this particular reaction? So our concentrations of our H2O, our CO, and again, on the other side here, we have our H2 and our CO2. Well, since the reaction is heading now, because we sort of forced it that way, towards the product side, we should expect an increase in the amount of H2 that's being formed. We should also expect an increase in the amount of CO2 that's going to be formed. Again, because we're sort of forcing the forward reaction to take place. But what does that mean for CO? When we look at the amount of CO, remember, in order to make our products, we do have to combine these two things to make our products. So if we're forcing that forward reaction to take place, we would then expect the amount of CO to start to go down because, again, it's actually making some product. Now, water is kind of an interesting one in this sort of question. And that is because what you will typically see, probably, if you were sort of monitoring the actual numbers, is because you added more H2O for water, you would initially see an increase in the amount of H2O because you artificially added it. But then once it starts reacting with the CO, you should start to see the H2O amount come back down. And in a lot of cases, if you were to do something like this in reality, you might actually see the H2O concentration actually end up higher than it started with. And that's only because you added it, so you added more to it. So you kind of artificially rose the concentration. But the pattern that you should see in terms of that guy is it should definitely go up because you added it. But then as it starts reacting, these two guys, you should then start to see it kind of work its way back down. And again, it may actually end up being, a little bit higher than it started with. Any questions on that? So let's see what would happen if we sort of did a little bit different if we added more H2 in this case. And if we added more H2 to this equilibrium, so the H2O, yeah, so the H2 on the last slide, again, because that's what we added. So we'll come back here just to see it. Because we added the H2O in this case, right? Just by the process of you literally picking up, I don't know if you could get a container of steam, but you picked up a container of steam and you added it to it. Just by that process, you added it. So automatically, just because you added it, the concentration of that should go up. But what's going to happen is as soon as it starts sort of reacting with the CO, which is going to do because you're kicking off this forward direction, what you'll see is actually the concentration of the H2O will also start to come back down. And the only reason I say that it may actually end up higher than where it started was because you artificially, if you want to think about it, went to the shelf, pulled it off the shelf, and kind of dumped it in. So you artificially increased it. But then as the reaction would start to take place, it will start to work its way kind of back down. And depending on how much you would have added to it, like I said, you may, in the case of water, actually see it end up being slightly higher than it started with. It may actually get lower, but you may, in some cases, actually see it ending up being a little bit higher than it started with. And you got to kind of put a little asterisk next to that because, again, it was artificially sort of added by you. So you artificially made it really high to begin with. So it will still work its way back down, is really what you'll see happen with it. Other questions on that? All right, so now if we look at our same sort of equilibrium, and this reaction is at equilibrium. In this case, we're going to add H2. So again, same idea here. If we add the H2 to the right-hand side here, what we should expect is sort of the same situation that we saw with the water. By adding more H2, that's going to provide more H2 to react with CO2. And because there's a greater amount of H2 at this point, because again, you kind of artificially went and I don't know where you grab a thing of H2, but I guess so, and you just added it to it. What that's going to do is actually kick off the reverse reaction to take place. Again, because we have a greater amount of H2 and CO2, so they're going to combine and really kick off again that reverse reaction to take place. Which means if we think about what's going to happen to our H2O concentration, we should expect it to go up because, again, the reaction is heading in that direction. We also should expect our CO concentration to go up as well for the same reason, because we're sort of kicking off this reverse reaction. In terms of our CO2, again, would we expect to actually see it start to decrease? So for the same reason, in order to make our reactants in this case, we need some H2 to react with some CO2. So we need these two guys basically to come together. So we are using up some of our CO2 to make our H2O and CO in this case. And then in terms of the H2, much like what happened and what we just talked about with the H2O, because you added it, you would initially, right off the bat, see an increase in it because, again, you artificially added it. But then as these two guys start to react, should see it come back down. So again, it may be a situation in that case, like we were talking about with the H2O in the previous example, that you may actually see it end up being a little bit higher than it started with. And again, that is mainly because you took it off the shelf and you dumped it into this reaction. So again, you artificially increased it, but really what you'll be seeing in terms of what's happening is it will start to work its way basically back down. Any questions on those two? Now, when we do have a reaction that reaches equilibrium or a reversible reaction, there is a sort of expression that we use to sort of describe it. And that expression is what is known as the equilibrium constant. And the equilibrium constant is capital K. And if you take 1B, it is all you talk about in 1B, pretty much the entire semester. So the equilibrium constant is capital K. And to calculate the equilibrium constant, we essentially take the concentration of our products divided by the concentration of our reactants. And when we see the little bracket like this, this means concentration. Oops, concentration. And usually that's molarity, which is moles per liter. So is usually what we will see. And there's an important thing here. When we do our products over our reactants, we actually do take the coefficients from the balanced equation, and they become like the exponents in our expression. So again, that's an important aspect of calculating K, is we take the coefficients as our exponents. Now, K is one of the few things sort of in chemistry that does not have units. So K is just a number. And it is an equilibrium constant, which means no matter what concentration of reactants or products that you start with, you could start with, say, 2 of A, 4 of B, 3 of C, and 5 of D. Or you could just start with 10 of A and 6 of B. When those reactions reach equilibrium, the value of a K will be constant. So that's also sometimes a hard concept for people to understand. It is a constant value. And sometimes when people think, well, how could that be if I start with 10 of this guy one time and 6 of this guy, or if I do like 9 of this guy and like 8 of this guy in another reaction, my K value will be the same no matter what, and it will be. So what happens when this reaction reaches equilibrium is when it reaches that point where the rate of the forward reaction equals the rate of the reverse reaction, and it comes to equilibrium, the proportion, if you will, the ratio of products to reactants will typically always be the same number, which is why it's a constant. The only thing that will actually affect the value of the equilibrium constant is temperature. So you could change the concentration of your reactants and products all you want all day, but if you keep the temperature constant, you will always hit the same K value for that reaction. But if you change the temperature, the value of K will change. So again, what that means is, let's just say, I'm making up this numbers. At a temperature of 25 degrees Celsius, for this reaction, we have a K value of 5. And at a temperature of, we'll go 45 degrees Celsius, we will have a K value of, say, 25. Okay. What that means is at 25 degrees Celsius, no matter what combination or amounts of reactants or products that you put together in this particular reaction, when it eventually hits equilibrium, the ratio of the products to reactants will always equal about 5. It should be really constant. Then if you take the same reaction and you raise the temperature to 45 degrees Celsius, again, no matter what combination of reactants or products in terms of concentrations that you start with at 45 degrees Celsius, it will always come to that ratio of basically 25. So when we say that temperature affects the value of the equilibrium constant, what we mean is in comparison between say a temperature of 25 degrees and a temperature of 45 degrees, you will have two different equilibrium constants. But if you run an experiment, 7 different trials with 7 different starting amounts, or 4 different starting amounts, but you keep the temperature at 25, they will all, for all 7 of those experiments, if you calculate the equilibrium constant, should always hit the same number. Question on that? Now, when we look at these reactions, there are a couple of things that are not included in an equilibrium constant. And that is solid and liquids are not included in the equilibrium expression. And that's for 2 reasons. A liquid like pure water, for example, in the liquid state, it pretty much is a constant concentration throughout. The concentration of it really doesn't change or anything like that. So if you happen to have any of these guys in this reaction that has an L symbol next to it, that's a pure liquid, you would not include it. The other thing is a solid is not included. And kind of the same reason. If you have a solid, it's just kind of sitting there on the bottom. And in its solid state, it's really not participating very much at all. In order for it to participate, you would have to dissolve the solvent, the solid. And when you do, you will actually get something that is now aqueous, which is included in the equilibrium constant. And gases are also included. So when you do the equilibrium expression, or the K, these are really the only things that should be included. Obviously, gas molecules, just by their nature, are flying around. So they're constantly mixing. They're constantly sort of participating with each other. Aqueous guys, which would be in a solution, the ions, for example, are floating around. So they're constantly moving around. They're able to really participate. But again, if you have a solid, it's just kind of sitting there like a rock on the bottom, not really doing much. The only way it could participate is you would have to dissolve it. Then it would no longer be a solid. It would be aqueous. And again, a pure liquid like water in the liquid state won't change its concentration very much. So things that are S's and L's, you do not put into this expression. Things that are aqueous or gas, you do put into that expression. So here, if we look at this, we can write the equilibrium constant for this reaction. Again, this is our products. Over our reactants. And just as we talked about before, we want to make sure that we do incorporate the coefficient. So that is where that 2 comes from, right there. And so that's the concentration of our NH3, which is a product. Again, it's a gas here, so it is included. Divided by our reactants. So our first reactive is N2. Coefficient here is 1, which is why we don't see a number here. It's just assumed to be 1. Times the concentration of our H2. The coefficient here is a 3, and that is what the 3 is for here. So that's basically what the 3 is for. This is, and again, we won't get too much into this, but there are different types of K values, and this is what is sometimes referred to as the KC value. C for concentration, because you're doing the concentrations of products over reactants. There's all kinds of K values, again, pretty much the entire semester there in 1B. We talk about KC, KP, KA, KB, KSP, KW, KF, it just goes on and on. There's all these different types of Ks, and they're really all the same thing. They're really all just equilibrium constants but there's slight variations on these different things. So sometimes you'll see people say this is the KC, and the C really just sort of stands for concentration. You could, again, do one which we're not going to get too much into, which is known as the KP. Because all these are gases, you could write the pressure squared of NH3 divided by the pressure of N2 times the pressure cubed of H2. So these are the partial pressures. Since we use pressures instead of concentrations, you could, for this particular reaction, write what is known as the Kp value, which is also an equilibrium constant. It just deals with pressures. So if you were to do the calculation for the Kp, you would use something like atmospheres, which is a unit of pressure. If you're obviously going to calculate the Kc value, you would use something like molarity, which is obviously a unit of concentration. Any questions on that there? Now, as I mentioned, K always has the same value at a given temperature, regardless of the amount of reactions or products that are initially present. And again, that is something sometimes people have a very hard time sort of understanding or comprehending because of that. But again, as long as you keep the temperature constant, no matter how much you start with in terms of your reactants or products, it will always come to equilibrium with the same ratio of products to reactants. Again, if you do change the temperature, the K value will change. And when you do see a K value written for a reaction, so for example, if we had our generic guy, K value is 20. This K value that would be specified is for a specific temperature and also exactly how that reaction is written. So it's not for the reverse reaction, it's exactly for whatever is on the reactant side, whatever is on the product side. That is essentially what the K value basically is there for. Let's though talk about really quick before we continue on what sort of the K value actually kind of means. So since our K is calculated as our products divided by our reactants, if we have a K value that is large, what that should mean is when we reach equilibrium, we should mainly have products. How do we know that? Just mathematically speaking, in order to get a large value of K, this guy would have to be large, right? And this would have to be small, right? So that means that the ratio of products would have to be large at equilibrium to the ratio of reactants. Now, the opposite is true if we calculate K and it's a small value. What that means is when we reach equilibrium, we will mainly have reactants. And again, just mathematically thinking about it, that means that this number here would have to be large. This number here would have to be small, right? Take a small number divided by a large number, you get a small number. And we can actually use the K value to help us determine when we look at a reaction, what we should expect to see there when it does reach equilibrium. So you may ask yourself, what is sort of considered a large value? What's considered a small value? Now, a large value of K is a very large number of 1. So basically 1 is considered a large value K, or really anything above 1 is considered a large value of K. Anything that is less than 1 basically is considered a small value of K. The reason 1 is because if you had 1, the only way you could get 1 is you need to have almost equal products and equal reactants, right? And that would get you 1. So obviously, if you get to a larger value than 1, then that means you have more products than reactants. And if you had a smaller value than 1, you would have more reactants than products in that case. So in our made up one here, where we have an equilibrium constant of 20, what that essentially means is when we reach equilibrium, we would expect to have mainly products. 20 is a pretty good value, pretty large value of K. And we would expect that when we do reach equilibrium, we would have mainly products there. But remember, again, it is still a reversible reaction. So although we may have mostly products there at equilibrium, it does still mean that we have some of these guys still there as well. So otherwise, it would be just a one-way reaction. There would be no back and forth. So even though we could use the equilibrium constant to tell us that we should mainly have products at equilibrium, or we should mainly have reactants at equilibrium, we still will have both at equilibrium in most cases. I mean, you could and potentially, you know, have something that has a super large value of K, which essentially would mean you pretty much have almost 100% onto the product side. But even in that case, you would still have, even if it's a very, 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 very small amount there, you would still technically have a small amount there of the reactants at equilibrium. So for example, if you had a K value that was like 1.5 times 10 to the 13, pretty much, or to the 30, right? 1 times 10 to the 30. Pretty much what that means is almost everything's on the product side. But if you were to do a calculation, perhaps you would find that on your reactant side, maybe you have a concentration of like 1 times 10 to the minus 18, which is essentially point and then 17 zeros and like a 1, right? So essentially, you don't really have much on the reactive side, but technically speaking, you still have just a smidge there. And same thing would be the opposite of that if you had something that usually if you look at the K value, you got more of a negative exponent. If you had to the minus 24 or something like that, what that would mean is the opposite, that you would mainly have reactants there. And this reaction would essentially, you know, say this was to the minus 34, the K value. And pretty much the reaction is staying over here on the reactant side. And you probably have mainly reactants present at equilibrium. But even still, you would still have a little bit of those products that would still be there. Any questions on that there? So if we look at this equilibrium expression here, obviously this box, so we'll just kind of go through how we got to that guy in the box. Again, if we're going to write the equilibrium constant expression, it's our products divided by our reactants. So on the product side, we would have H plus, the coefficient is 1, so we wouldn't put anything there. We would have it times our acetate coefficient, also 1, so we wouldn't put anything up there. Divided by our reactant, which is our acetic acid, also coefficient here of 1, so we wouldn't put anything there. So this is what it should look like, not the opposite. That would be reactants over products, so that one's wrong. No plusing or anything like that. So always products over reactants when you write that. And obviously, if you are given the equilibrium constant, so since this is an equilibrium constant expression, the values that you would need to actually put numbers into here would be not the initial concentrations, but you would need the equilibrium concentrations of each of those guys to actually put into this expression to actually get a number, which is what we got going on here. So let's take a look at this one here. For this reaction below, given the equilibrium concentrations, calculate the value of the equilibrium constant. So again, we would look at the balanced equation and do our products, which in this case is NO2. In this case, we do need to square it because of this coefficient. We need to divide it by our reactants, which is N2O4. Again, the coefficient here is 1, so we don't put anything here. Now, we were told that these are the equilibrium concentrations of each of these guys. So that is what we would want to put in here. So like it shows on the bottom there, we would take our NO2 concentration at equilibrium and put it in, again, remembering to square it, divided by our equilibrium concentration of our N2O4. Here again, we don't have to do anything with it because it's to the first power. So 0.06 squared divided by obviously what we got there gives us an equilibrium constant of 0.065 like it shows on the bottom. First off, any questions on the setup there or how to put the numbers in? Now, when we do look at this value, what we look at here in this particular case is we see that the equilibrium constant here is less than 1, which means if we had to guess when we reach equilibrium, we should mainly have products, mainly have reactants there. So again, that would allow us to do that. Yeah, so it's a good question. Probably for our purposes in this class, in most cases, it will probably be given to you, the equilibrium constants. We are going to talk about at the very end of this chapter how to actually calculate the equilibrium concentrations. So I'm going to say probably in most cases, but at the end of the chapter, we're going to talk about how to actually calculate them to a very limited extent. Again, these calculations, if you're not given the equilibrium concentrations, are quite complicated, some of them, and they are essentially what you do in 1B. So it'll be sort of like a preview of 1B towards the end of this chapter. So I would say most of the time they'll probably be given to you in sort of this chapter, I would think, but you may have to calculate it, and we're going to talk about how to calculate it at the end of this chapter if you're not given it. So if you are given the initial concentrations, you definitely cannot go into this expression. Again, they definitely has to be the equilibrium concentrations to do so. So we will talk about sort of a small case and more of a straightforward way of calculating them. And then you could save all the more complicated way for 1B when you take it, which there's a lot of complicated ways to calculate it. Other questions on this? So when we talk about equilibrium, there's a couple of different types of equilibrium. They're kind of like mixtures and stuff that we talked about. If you remember, a homogeneous mixture is one that looks the same throughout. So when we talk about a homogeneous equilibrium, what it essentially means is the states of everybody in that reaction are all the same. So these are all gases. So it's homogeneous. Again, everybody's in the same state. These are all aqueous ions that would be floating around in the solution. Again, they're all aqueous here, which means that they would all be homogeneous type equilibrium. And again, we could write our equilibrium expression for each of these. For the first one, it would be the NH3. We would square it because of the number, just like we saw earlier, our N2 and our H2, which would be cubed, again, because of the number. For our bottom one, it would be our H plus times our Cn minus. Again, each of these are 1. We don't have to worry about any type of squaring or anything like that. and divided by our HCN, which would also be 1 in this case. So again, a homogeneous equilibrium is one where we basically have everybody in the same state. In the top one, everybody's gases, they're all flying around together. The bottom one, everybody's aqueous ions, they're basically all floating around together. There's also equilibrium where we have what is known as heterogeneous equilibrium. And that's a case where we get things that are not all in the same state. So we have different states. And this sort of ties into what I was talking about earlier with our equilibrium expression. Again, if you come across anything that's a solid or a liquid, they really don't participate very much in equilibrium. So again, they're not included in the K expression. I will in just a second. I'll go back after this one. I think we're going to wrap up on this slide, so I'll go back and let you take a look at that in just a second. If we were to write our equilibrium expression here for our first one, it would still be our products over reactants. In the case of our products, we would not include this guy because he's a solid. We would include this guy. So we would take the concentration of O2 and we would cube it. Now we would normally take it over our reactants, right? But when we go to our reactant side, this guy is also a solid, so we would not include it either. So the correct K expression for the top one would be just O2 cubed. And if we do it for our bottom one, same approach, we'll take our products. So we will include our H2, and we will square it because of the number here. This guy's a gas, so he'll be included as well. And his coefficient is 1. Now, when we get to our reactant side, we have a liquid, which, as we talked about, would not be included. So this would be the correct equilibrium expression for the bottom one. This would be the correct equilibrium expression for our top one. Now, let's just say, for example, you had 2A plus 3B goes to 4C, that's a solid. And we wanted to write our equilibrium expression for this. The problem is, though, right, when we go to our product side, for this one, yeah, I did right here. So the 2 on the coefficient becomes the exponent when you do an equilibrium expression. So the 2 goes up there on top as the exponent. Yeah. So if we were to look at this one, when we take our products over our reactants, our product, yeah, the one on the bottom is for the top reaction, so that's for the top. Yep. And that's for the bottom. So when we look at our product side, though, it's a solid, so we would not include it. So the way we would handle that is actually we would do 1 over our reactants in this case. And it would look something like this. So if you happen to have a reaction where the product is solid or the product's all liquid, you basically do 1 over the reactants, and that would get you to your equilibrium expression. Question on how to write equilibrium expressions, sort of calculate the value of equilibrium expressions, sort of what it means. Okay, so we'll stop here today. Let's talk about some things that are coming up so everybody's on the same page. And why I do that, I'll flip back a slide. So I think that was the one you wanted to look at. So we moved, obviously, the exam from today to not Tuesday, Monday would be good, on Monday. So we will take the exam on Monday like we've done before. Again, a reminder that the exam will cover chapters 14 that we moved to that. So 14, 15, and 16. So none of this stuff here from chapter 17 will be on it. So again, 14, 15, and 16. So 14, I think, was like intermolecular forces, I think. Some of that heat of fusion stuff, if I'm not mistaken. I think 15 was solutions. And I think 16 was acid and bases. So that will be what will be on the exam. We'll probably do it like normal. So we'll have a maybe a short little lecture, maybe to finish this chapter here, or get through at least the Le Chatelier's principle part of it, and then we'll stop lecture a little bit early, and then you could start your exam around lab time and take it. So that'll take care of Monday. That will then leave us Wednesday as our very last lecture day, I believe. And we will obviously finish up any lecturing that we need to do here. What we're going to do, I think, is because we did not get to Le Chatelier's principle, which is the experiment, and since it was originally scheduled for this coming Monday, we're just going to move Le Chatelier's principle to next Wednesday. So we'll do it next Wednesday after we had an opportunity to talk about it. So there'll be no lab today in terms of anything you need to turn in. The last lab of the season will happen next Wednesday officially, I guess, which will be Le Chatelier's principle, or maybe I'll open it up on Monday. You could just do it sometime between Monday and Wednesday if we finish talking about Le Chatelier's principle on Monday, which I think we will. So sometime Monday or Wednesday, I'll open up that last lab. I believe the pre-lab for it is still due on Monday, so make sure you do that one as well. In terms of the homework, I did move the homework, I believe, to the end of next week, if I'm not mistaken, for those chapters. So don't forget about those as well. So for the lab today, again, I'll be happy. I'm going to open it in about 10, 15 minutes. And again, like I said, there's really no lab we're going to do today. We're just going to do it on Monday. But since we do have an exam coming up, if you have any questions or anything like that, I'll be there for the lab period in case you want to come and sort of ask some questions or anything I could help you with, and I'll do that. Yeah, our last lab is really, I think, 24. If I'm not mistaken, the truly last lab is 25. And in a normal situation, the last lab is like the checkout lab. It tells you how to check out, basically. And I think there's a few post-lab questions or something like that. So the last truly real lab is the Le Chatelier's principle, which is 24. And again, like I said, there is lab 25, but if you read through lab 25, it pretty much walks you through checking out of the lab. And I think there's like 2 post-lab questions or something like that. So I'll look at those post-lab questions and see if we'll do them or not. But really, there's no real lab for 25, or activity 25, I think it's called. Other questions on anything? So like usual, you'll be given your normal sort of information on the exam. You'll be expected to know it. Obviously, you're expected to do the problems and upload your work in a very timely fashion for any problems that have work associated with it. And again, you shouldn't run into any problems in terms of timing if you started around, obviously, when lab normally starts. But we will have a short lecture probably on Monday, and that'll probably be enough time to finish up talking about sort of Le Chatelier's principle. And again, I'll probably open up Le Chatelier's principle 24 experiment on Monday. It probably won't be due until Wednesday. And I'll give you some time if you want to kind of work on it and knock it out and stuff like that. And then I believe what's left, yeah, the final exam, which was my next thing I was going to mention. To my knowledge, we're still doing the final exam during the normal scheduled time. Again, I'm assuming that's what everybody else should be doing as well, so nobody runs into any type of conflicts or anything like that. So my guess is we're still going to have our final, which I believe it's Wednesday, if I'm not mistaken, correct? I think of that week. So I think it should be like 2 weeks from today, if I'm not mistaken. We'll do it when it's normally scheduled. There really will be no lab final, so there's no lab final for this class. There's just a lecture final, and we'll just take the lecture final, I'm assuming, just like we've done everything else, kind of on Canvas at this point and stuff like that. So We're down to, I think, 3 days. So we got 2 days next week, and then one more day, which is the final, which again, I think is the Wednesday. So I think it's 2 weeks from today. The final will be comprehensive. So it will cover all the chapters that we covered. So whatever that is, 16 or 17 chapters. So when you're studying for the final, again, you want to think about, some of the big topics we talked about, some of the stuff that maybe appeared on earlier exams will probably appear again, maybe not in the exact same format, but obviously the material and the topics will appear that. Yeah, I think we're going to start the final during our lecture time. And that way, and that's usually what we would have done during our normal thing. It was scheduled for our lecture meeting, which I think might be 10ish it starts. I think whatever it says on the syllabus is pretty much when we will kind of start the exam. So whenever it's scheduled, the final that it says on the syllabus, we're going to hold to that. Again, like I said, so that should hopefully not allow any type of conflicts or anything like that and stuff like that. But I think at like a normal situation, our final would start maybe a half hour earlier, I think in our case, maybe 10ish. Seems like a number I think seem to remember. But definitely whatever it says on the syllabus. All right, any other questions on anything? All right, so if you don't really have questions today, have a good weekend and everything. We'll see you Monday. Remember, the exam is on Monday. And again, we will have a short lecture beforehand. If you do have questions, I'm going to start the lab at about 12:15. You're welcome to pop in if you want to ask some questions. I could work something out on the screen or something for you. Just let me know. Otherwise, have a good weekend, and see you on Monday.